In today's video, we are going to be starting chapter 10, which is gas laws. So obviously we are going to be talking about gases. Today we're going to talk about some basic properties, and the main thing that we will be doing for this unit is the ideal gas law, which is a calculation. Part of that calculation is moles. So then from there, we'll also be doing some stoichiometry. All right, the things listed on this slide, I am not going to spend a huge amount of time talking about because you already should have some knowledge from Regents Chem, or you can easily use your book to figure out these things. So first thing that we will just briefly talk about is the definition of pressure. So the pressure of a gas comes from the particles colliding with the walls of the container. So if you have more molecules in the container, the pressure will increase because there will be more collisions. Additionally, at a higher temperature, the molecules are going to be moving with a greater average kinetic energy, so therefore they will be hitting the walls of the container with more force, thus increasing pressure. So if you're increasing the number of collisions or increasing the force of the collisions, you will be increasing the pressure. Another thing, this would be from Regents Chem, Boyle's law, Charles's law, and Gay-Lussac's law, that gives us the relationship between pressure, volume, and temperature. So for example, as pressure increases, the volume will decrease. So that is Boyle's law. As pressure increases, the volume will decrease. Charles's law is temperature. So as temperature increases, the volume will increase. They have a direct relationship, and that would be based upon the Kelvin temperature. So think about a balloon. If you heat it up, it will burst because of that increase in volume. And then lastly, Gay-Lussac's law is what we know as Avogadro's hypothesis, that equal volumes of gases, if they are at the same temperature and pressure, would contain an equal number of moles, thus an equal number of molecules. Another review from Regents is the combined gas law, P1V1 over T1 equals P2V2 over T2. The temperature for all of our gas law calculations must be in Kelvin. So we'll do a couple of practice problems on a worksheet applying that. And then the last thing that you are responsible for is knowing which conditions a gas will behave most ideally and least ideally. All right, before we get to any calculations with this unit, we need to be good at converting one unit of pressure into another. So as a reminder, 1 atm, 1 atmosphere, is equivalent to 760 millimeters of mercury. A millimeter of mercury is also equal to torr, so 1 atm would be equal to 760 millimeters of mercury, or 760 torr. And 1 atm is equal to 101.3 kilopascals, or 101,325 pascals. So 1 atm is equal to 760 millimeters of mercury, 760 torr, and 101.3 kilopascals. So all of those things are equivalent, and we will use them to convert from one unit to another. All right, so we are now just going to practice a couple of conversions to make sure that we are good with that skill. So we have 724 millimeters mercury. We need to convert it to torr, atm, and kilopascals. So first one is not really a calculation because millimeters of mercury is equivalent to torr. So if I have 724 millimeters mercury, I would also have 724 torr. All right, with the second one, we do have to convert. We take what we're given and put that over 1 like we always do when we are doing our conversions. We would need to do millimeters of mercury in the denominator and then the unit that we're trying to find, which is atmospheres, in the numerator. And we know from the previous slide that 1 atm is equivalent to 760 millimeters of mercury. So all we are going to do is take 724 and divide that by 760, and that will give us 0.953 atm. And then last one into kilopascals. So again, take what you were given, the 724 millimeters of mercury, put that over 1, and we know that millimeters of mercury need to go in the denominator so that they will cancel. Kilopascals will go up on top. So we know that standard is 760 millimeters of mercury. Standard is also 101.3 or 325 kilopascals. So those would be equivalent. So I could do it with just one conversion factor. You also could have gone to ATMs and then from ATM gone to kilopascals and used 3 parentheses total. Either way, we will end up with the same answer. So we do the 724 divided by 760 and times 101.3, and that would give us 96.5 kilopascals. Now, alternately, you could have just started from the atmospheres and went to kilopascals that way too.